Patrick tonight from GetML, and he will now take over with his talk about why relational learning matters. I would say I stop the screen sharing, Patrick, and the stage is yours.
Hello, can everybody hear me? I hope everybody can hear me.
Yes.
Yes, very good. So I'm going to share my screen. Just give me a second there. So now hopefully you should be able to see this. And obviously we'll get straight to the presentation. So can everybody see the presentation?
I see it, yes. Maybe you can write also in the chat if anyone.
Okay, well, I can't see the chat. So if any questions, you'll have to collect them and you can interrupt me anytime.
I will, but everyone says yes. Go for
Everyone says yes. I'm happy about that. Very good. Okay, let's get right to the talk. Imagine you are a data scientist working for a company, and for most of you, that shouldn't be too hard. And imagine that your boss comes to you and he or she says to you, well, can you build a model that could predict customer retention, customer churn, that will predict which customers are going to leave the company and maybe go off to a competitor? Well, also, your boss is going to present you with these simple tables. This is obviously a fictitious example, but your boss will present you with these three simple tables. The first table is, well, that contains your target values, whether a customer has left the company, yes or no. So this is what you want to predict. And then, of course, you have a customer ID. And then, of course, for your customers, you might have different transactions. So you can see what transactions they have done with your company. And maybe you also have a table that is called complaints. Well, whenever a customer has complained about your company, about some service that you didn't like, well, that is in the complaints table. And what you will find is that this sort of relational data, this sort of format, won't really neatly fit into your favorite machine learning algorithm like XGBoost and so on and so forth. You need to turn this into a flat table. The first thing that you need to do is to build features. And a couple of features that you could come up with for this particular problem is, well, how many transactions has the customer conducted? How many transactions has the customer conducted the last 30 days? How about the last 90 days? Well, what is the total transaction volume? How much money have we made on this customer in the past? What is the total transaction volume for transactions in the last 30 days? And so on and so forth. So these are just a couple of ideas of the kind of features that you could build if you wanted to predict customer retention. And as a matter of fact, it's not just customer churn, it's not just customer retention. There are actually many use cases that you will see in the real world that involve this kind of relational data. Another thing you might think of is targeted advertising. So for instance, you have a new product at your company and you want to maybe promote this to your customer, but you don't want to just send everybody a letter. Instead, what you want to do is maybe find out what kind of customers might be most interested in this sort of product. And again, you might have a customer history. You might take a look at, well, what kind of customers, who has bought somewhat similar products? And maybe that would be an interesting feature to pick down as well. Or maybe if this is a targeted advertising for the web, for Google Ads, you can sort of take a look at the website history, what kind of websites they visited, and so on and so forth. But another thing that you might think of is fraud detection. So imagine you are a bank and you want to predict credit card fraud. And now there's a transaction from somebody who wants to withdraw a large amount of money somewhere in the Congo. Is this a suspicious transaction? Well, it depends. What most banks would do, of course, in Germany, whenever it's abroad, it's a suspicious transaction and they won't allow you to withdraw money. But I think if you want to have a good customer experience, what we want to do is to build something that is a bit more complex, that is a bit more advanced system. So you might want to take a look at, well, maybe this person goes to Africa a lot, travels to Africa a lot, and that person often withdraws money from Africa. Well, in that case, it's really not that suspicious. And also, if that person is very rich and just has a habit of withdrawing large amounts of money, well, this particular transaction really isn't that suspicious at all. But if you want to build an intelligent fraud detection system, again, you have to take a look at the customer history and build intelligent features from that. Another topic, if you're an online retailer, you might be thinking about product returns a lot. So people, they order something online and then they send it back if they ask for the money back. In online retail, it's obviously a big, big problem. And maybe what you want to build is some kind of prediction system for that. So you have a shopping basket, you have a bunch of products in the shopping basket, and for every single product in the shopping basket, you want to predict how likely is it that the customer is going to return that. And again, what would you do? How would you predict that? Well, you would take a look at the other products in the basket. You would take a look at, well, are there many similar products in that same shopping basket? And again, this is very, very relational. Finally, you have something like customer lifetime value. You want to predict how much money are we as a company going to make on that customer in the future. Obviously, if this is a very valuable customer, maybe we'll treat them differently. And the final example that I would want to give you is time series in general. You will find that relational learning, because it is more flexible than classical time series analysis, it doesn't have the same assumptions the classical time series analysis makes, is actually a very, very good tool for time series as well. Now, I won't go into that too deeply because I actually, at the end of this presentation, I have a little live session for you, which involves the time series data set. So for now, you just will have to believe me. Then by the end of the talk, we'll get back to that. Okay, so now that we have established that there are many, many use cases that involve relational data, whenever you do a use case like this, you will be presented with the predictive analytics workflow. So what you will have in the beginning are all these kind of tables that are related to each other in a relational manner. You've got this relational data model, and then there's one table that contains your target value. And of course, what you want to do is to turn all of this relational data into a flat feature table. And this flat feature table, you can do some simple transforms on that, and then insert this into your favorite machine learning algorithm, like XGBoost, like LightCBM, like CapBoost, like scikit-learn, and whatnot. So there are many, many things you can do there, and then of course this is going to give you prediction. But in order to get from the relational data to the flat feature table, you would have to engage something in something called manual feature engineering. And for these sort of projects, the fact is you will spend most of your time on this part, the manual feature engineering. And the generally agreed upon number is that 80% of your data science project on this kind of data will be spent on feature engineering. And that is a bit of a problem if you think about it, because I haven't met too many data scientists who like doing this. Most of the data scientists, they like doing this. They like the machine learning part. They always want to get to the machine learning. And they sort of like to skip this a bit. But that's a bit of a problem. Because if you skip that, you're not going to get a very good model. You're not going to get a very good prediction. There's only so much that you can do, that you can fine-tune if you don't really have good features. So this is really where you want to be spending most of your time. Now, there's another problem with that, other than data science not liking manual feature engineering. And that has to do with cost. There's a very, very interesting survey that I found last year. It was made last year among German companies. And these companies, they had a minimum size. So it's not just any company that participated in the survey, but there was a minimum size. And by the way, it's very interesting. I've got the link there. It's very, very interesting to look at this after the talk, because there are some, it's very interesting. There's a lot you can learn from that survey. In any case, among those German companies that took part in this survey, 73% think that AI, quote unquote, is the most important technology of the future. And what you will find from that survey, when they say AI, what they actually mean is machine learning. So you read AI, but then what they actually mean is machine learning. But of those companies, of the companies that were surveyed, only 6% actually use machine learning, which many of them think is the most important technology. So as you can see, there's a big gap there. But you can actually dig a bit deeper here. You can actually take a look at, well, those 6% of the companies that actually use machine learning, what is it that they actually do? And what you will find is that in over 80% of the cases, what they actually do is exactly the kind of use cases I've discussed that are related to customer data, like customer retention, targeted advertising, and so on and so forth. Exactly the kind of things we just talked about. And if you think about it, well, it really makes a lot of sense that this is what they should focus on. This is how you get started. Because you think about it, all of these companies, they already have their customer relationship management database. All of the data that they need is already there, but they don't do anything with it. So if you want to introduce them to machine learning, and you want to start with the low-hanging fruit, well, you're going to work with the data that is already there. You're going to work with customer relationship management. And of course, every company has customers, and they would like to keep their customers. So it just makes a lot of sense to get started with these sort of things. And once you've got them started, you've got them hooked on these sort of customer-centric use cases, then you can maybe go on and do more advanced stuff like natural language processing and deep learning and these sort of things. But this is just the low-hanging fruit. It just makes a lot of sense. But again, only 6% of the companies actually do even this kind of very basic stuff. So one of the main reasons for that, why do so few companies use machine learning, even though they think it's the most important technology in the future? And the main reason is, well, they don't have the time, they don't have the people, and they don't have the money. So the question is, what can we do to make machine learning, to make data science more accessible to these companies? Well, very simple. We cut the cost. We need to reduce the time and the cost that it takes to do these sort of projects, to do the kind of project that get them started with machine learning. And how do we do that? Well, very simple. We take the most time-intensive task of the predictive analytics workflow, which, as we just established, is manual feature engineering. We take that most time-intensive task and we automate it. And that will then radically reduce the time and the cost that it takes to do like a predictive analytics project of the manner that we have just discussed. And yeah, that is the way to go. And that is what automated feature engineering and relational learning in general is all about. So I would assume that most of the people who are listening to me are data scientists. So if you really care about data science, if you want to have an impact with your data science, if you want to make data science and machine learning accessible to companies and organizations who otherwise would not have access to it, you should really care about relational learning, and you should really care about these kind of things, this kind of stuff, because this is what is going to help you really make an impact, really make a difference with your machine learning skills. So I hope that I have sparked some interest in the topic of automated feature engineering, and now I sort of want to dig a bit deeper and sort of talk about what are we hoping for when we talk about automated feature engineering. So obviously our objective is to automatically generate a flat table from a relational data model. This is what we've just talked about. Automate the process of manual feature engineering. The next thing that I would argue is very important is I want to be able to express the features in SQL. Yes, so I want to be able to express the features in SQL because I as a data scientist, I want to be able to look at the features. I want to be able to study them. I want to be able to figure out what is going on. And maybe also, I want to be able to share my features with the customer, with the business people, because that is how you build trust in the model. When you tell them, okay, these are the kind of features that we use, and then they tell us, yeah, that really makes a lot of sense. In that case, yeah, that will build trust in the model, and they would be more likely to use it and use it productively. The next thing is we don't want extensive fine-tuning. The reason I bring that up is because when we got started, we started on this journey. Our first instinct was to use deep learning. But the problem with deep learning was, yes, it worked well, and yes, we got good predictions, but we spend a lot of time fine-tuning our deep neural networks. And that was a bit of a problem because the entire pitch that I just made to you is, well, this is going to save you a lot of time. But if the time that we spent using on manual feature engineering is instead spent on fine-tuning our deep neural networks, well, that's a bit of a problem. And the next problem, by the way, with deep learning is that we can't express the features in SQL. So that's a problem as well. And finally, what I'm hoping for algorithms that are scalable to large data sets. Okay, so the world of relational learning, the academic literature of relational learning is over 20 years old. There's over 20 years of research on this topic. So obviously there are lots and lots of approaches out there that I could share with you. But what I want to do is I want to focus on approaches that meet these objectives. So everything else, of course, I want to mention is also out there, but we are going to focus on these things tonight. So what are the prerequisites? What would we expect our users to provide us? Well, first of all, we would expect them to provide us with an abstract data model like this. Oh, I'm sorry. Okay. I would expect the users to provide us with an abstract data model like this. The user would also clearly have to define a target variable. So the data scientist has to know what he or she wants to predict. But other than that, we do not require, and we shouldn't require, in automated feature engineering, very extensive domain knowledge. So the data scientist does not have to have a deep understanding of what drives customer retention in the banking sector, or how product returns in online retail work. The data scientist would only provide the data model, and then the data would speak for itself, and the automated feature engineering algorithm would automatically generate the features that we need. This is what we're looking for, this is our wish list, and this is what we hope to accomplish with automated feature engineering. Okay, so the first algorithm, the first approach that I want to share with you is called propositionalization. It's a very big name, but it's actually a very, very simple concept. So the idea is you just try everything. So you've got your data with several columns, and you've got a bunch of aggregations, and then you just apply all of your aggregations to all of your columns. So you take the average of column 1, you take the sum of column 1, take the count, you take the max of column 1, take the minimum of column 1, and so on and so forth. And then you move on to column 2, and then again you take the average of column 2, the sum of column 2, the max of column 2, and so on and so forth. I think you get the idea here. So again, I just want to quickly summarize the recipe. What you do is you just try all possible combinations of aggregations and the columns that you have by brute force. Optionally, what you could also do is maybe apply some simple transformations. So for instance, if you have a timestamp, say, what you could do is you could extract the time of the day, you can extract the day of the week, and have that as features, have that as columns as well. Maybe, if you're really courageous, you could allow for some really simple conditions on top of that as well. But again, these sort of simple conditions in your SQL features are very, very likely to sort of make your feature space explode. You'll have lots of features. So really keep it very simple here. And optionally, I actually would strongly recommend that you do this. You should also do a feature selection. So it is very, very likely that you're going to end up with lots and lots of features if you use propositionalization. And most of these features are going to be garbage. So you really want to pick out the features that you really need. Otherwise, these features are going to clog your data science pipeline. So I want to quickly discuss the pros and the cons of propositionalization as an approach. So the first pro is it's very simple. Get very simple interpretable features that are very similar to the kind of features you would probably build by hand. And this is a very big pro. You really shouldn't underestimate that. The power of interpretability, the ability to go to your customer and tell them, look, these are the kind of features that we have built. And it's not witchcraft, it's all there. The next thing is it's very, very easy to implement. So when I talk to people and when I share with them what it is that we do, talk to data scientists, what I often get is that they tell us, oh yeah, back at my old job or back at my current job, we've really done something similar, just for us, just our own homemade tool, so to say. And then when you dig a bit deeper, it always turns out to be that they have used the propositionalization approach. They hardly ever know that what they do is called propositionalization, but it is what they do. And the even better news is, actually, you don't have to do that yourself. There are many, many implementations, some of them open source implementations out there that you can use. So the most famous one is clearly feature tools. Then we also have TS Fresh and H2O, so they have automated feature engineering, particularly for time series. There's also Expanse Analytics, there's Data, and then there's also GetML. So just full disclosure here, by the way, we do have a startup that is related to automated feature engineering. It is called GetML. So just in case you wondered. But when I talked to Lara initially about this talk, what we agreed upon is that this was supposed to focus on the method. So there's not supposed to be a pitch talk for my company. I really hope you don't perceive it that way. I really want to keep this academic. I want to introduce you to the tools that you can use to automate feature engineering. And if you go away from this talk and you realize, well, actually, there is a very good alternative to manual feature engineering, then I'm happy with that. That is really my goal that I want to accomplish. And it's not supposed to be a promotional talk for my company. I really hope you don't feel about it this way. Okay, let's talk about the cons of feature explosion, the cons of propositionalization. So the first thing is feature explosion. I've sort of hinted at that earlier. So the problem that you have is it will generate many, many, many features. And you will have to deal with that. That is a problem you will certainly have to deal with. The next problem is, I said it's easy to implement, and that is true, but it's also hard to implement efficiently. There is a very, very big difference. So what we did is we had a whole bunch of experiments. We had a whole bunch of benchmarks on that. Well, we benchmarked an efficient implementation of optimized C++ code against something that you could build on top of Pandas or Apache Spark, or data tables in R, and so on and so forth. And what we found was that an optimized C++ implementation can be more than 10 times faster than something that you would build on top of Pandas. Also, what we also found was that the memory consumption of something written in C++ is just a fraction of what you would get about something that you would build on top of Pandas. So you don't really have very big data sets. Well, that's okay. You can do this yourself. You don't really have to care about efficiency that much. But if you have bigger data sets, if you want something that is more stable, well, you will find this is actually not very easy to implement. And maybe you can use some of the tools that I've put. The next problem with propositionalization is that these features are very simple. And by design, they cannot capture very complex relationships in the data. And also, as I've hinted before, well, you will get many garbage features. And most of the features are just going to be useless. It's just a small fraction of the features that are actually going to generate the prediction for you. Okay, so now that we have discussed the simplest approach we could possibly think of, let's think about what we can do to make this a bit more advanced. What would be a bit more of a machine learning approach to feature engineering? What might that look like? And the next approach that I want to share with you is called MRDTL, or Multi-Relational Decision Tree Learning. And as the name implies, the idea really is to apply decision tree learning to the concept, to the challenge of automating feature engineering on relational data. So the first step of MRDTL is actually very, very similar to what you would get with propositionalization. So you would start with some sort of column, you start with some sort of aggregation, start with some sort of join key that you would group over. So that is all very similar to propositionalization. But then you get to the next step. Then what you would do is you can add in these sort of conditions. And so for instance, you could limit the transactions to the last past 90 days, and you can limit the transaction types to these three transactions. It's a completely fictitious example, but I really think you get the idea here. And the way MRDTL does that, the way MRDTL goes the next step that propositionalization cannot do, and add in these sort of more complex conditions on top of features is by tree-like and greedy algorithm. So you start the very same approach with propositionalization. You pick an aggregation, you pick a column to be aggregated, and then you just add different conditions on top of your features. So maybe you limit yourself to the past 90 days, and then you also try 91 days, 92 days, and so on and so forth. So you try out all of these different conditions. And every time you try the condition, there's some sort of optimization criteria. There's some sort of loss function that you have that you want to optimize. And then of all of these conditions, you keep the condition that yields the maximum improvement. And then that condition becomes part of your feature. It remains part of your feature forever. And then you go back to step 2. You try adding more conditions on top of that. For each of these conditions, you calculate the maximum improvement. And then you keep that condition as well. And then you keep on repeating that until you reach some sort of stopping criteria and you decide, okay, now the feature is complicated enough. Okay. By the way, if there are any questions, Lara, please feel free to interrupt me. If you think I'm going to pass anything, just write it and then Lara will interrupt me. Again, I want to share the pros and cons of this approach with you. So the obvious pro is it can capture more complex relationships than you would get with simple propositionalization. But at the same time, the features are reasonably close to manual features. So if you look at something like this, if you look at this kind of feature, yes, I mean, this may be a bit more complicated than what you write by hand. I don't think that you would write in 3 different transaction types unless there's a very, very clear business logic to choose these 3 transaction types in particular. Chances are you're not going to write something quite as complicated as this. But at the same time, when you see this, when you read this, you can still sort of get an idea of what is going on. And it's still reasonably close to something you would write by hand. So, that's a pro. On the con side, we still have the feature explosion problem. And I will actually discuss that just a bit later at greater detail. It is also very hard to implement it efficiently. If you read the papers, the first paper on MRDTL came out in the late 90s, but after that, there were 10 years of additional papers that took MRDTL and discussed, well, how can we make this more efficient? How can we overcome efficiency challenges that we have with MRDTL? So this is very, very difficult to implement efficiently. And also because it is a greedy algorithm, as with all greedy algorithms, there's actually information that you might lose due to this greediness that you have. Okay, so now we have talked about trees. Now we have talked about how we can apply trees to relational learning. And of course, once we've talked about trees, there's a next logical step that we can do, which is to use forests. Of course, we don't want to have just one feature, we want to have several features. And a very, very beautiful thing about trees and applying these sort of machine learning concepts to relational data is that you can piggyback on top of existing paradigms in machine learning. And one of the most popular paradigms in machine learning, of course, are random forests. I'm sure that many of you would have used random forests before to generate a predictive model. They are a very, very popular algorithm. And so all we have to do is to take this idea of trees and then combine it with the idea of random forests on a relational data set. And the most popular approach to do this is called FORTH, which is short for first order random forest. So the first thing I should have to tell you about FORTH is that the trees that they use are actually a bit more complicated than MRDTL. So as I mentioned earlier, MRDTL, you just have one aggregation. So there's just one aggregation, and then on that aggregation, you add conditions. With FORTH, the trees are a bit more complicated. So they have many aggregations. They have aggregations at every single node of the tree. So you maybe start with, okay, well, what if the sun column 1 is greater than 3, and if that is true, you would go to the next branch and then decide, well, if the average of column 2 is smaller than 6, but only where column 3 is CC. So these sort of aggregations can also be refined. You can also add conditions on top of that. So basically what you would do here is at every node of the tree, you have an MRDTL feature. So this is somewhat more complicated, but at the end of the day, the idea is absolutely the same. It's quite similar to MRDTL, only again, the trees are somewhat more complicated than we have here. So that's the first element. That's the first element of 4. You have somewhat more complicated trees than we get with MRDTL. And the next thing is obviously what makes random forest, which is stacking, bootstrap aggregation. So you've got your training set on top of which you train your machine learning algorithm, and you sample from that. You sample from that training set to add randomness. And of course, every time you train a new tree, you would get a new sample. You get a new sample from the training set to train your new trees. And this adds an element of randomness. This is what random forest is all about. And then, of course, you can build as many trees / features as you like. And then you can use these features to generate a prediction. So let's again talk about the pros and cons of fork. So the first pro about fork that I really, really like is that it builds on a very, very successful machine learning paradigm. Random forest is one of the most cited papers in machine learning, and of course, making use of that and using that for relational learning and for this problem that we have here, well, this is obviously a good way to go. Also, much like MRDTL, it can capture more complex relationships, and you can, of course, because it's random forest, build any number of features you like. On the con side, we also have the feature explosion problem. This is going to be the next slide. It's also hard to implement efficiently. In fact, it's just as complicated as MRDTL and more. And of course, as always with trees, you might lose information due to greediness of the approach. Okay, so I've mentioned the issue of feature explosion a lot. So I want to sort of take a step back and discuss that problem at greater detail before we go into the next algorithm. What I've written here on this slide is a very, very basic, very sort of generic feature that you might either train using an algorithm, or you might also write this by hand. If we write features by hand, this is what it looks like. Some sort of aggregation over some sort of column, and then we apply some sort of condition on that based on some sort of other column. Let's take a step back and think about that for a second, what we do here. So let's just say there are 10 columns in total that we can aggregate. So what is the number of possible combinations that we have here? Well, of course, there are 10 columns that we can put in our aggregation. And then there are 10 columns we can put into our condition down here. So 10 times 10 is 100. Okay, fair enough. What if we have 100 possible columns that we can aggregate? Well, again, we can add 100 columns into our aggregation. We can add 100 columns into our condition, and then it's 100 times 100, which is 10,000. And what this basically means is that the feature space grows quadratically with the number of columns. And from the standpoint of computational complexity, that is very, very bad. You've got a very, very big feature space that you have to search through here. And that really doesn't matter whether you do it by an algorithm or you do it by hand. This is going to be a problem that is going to follow you. Particularly if we talk about these sort of customer relationship management databases. These CRM databases, they often have many, many, many columns that you have to deal with, that you have to put into your model. And you have to find a way to deal with them. And that means you have to have an algorithm that is sort of more robust against feature explosion. And this is exactly the idea of the next algorithm that I want to introduce to you. So the next algorithm I want to introduce to you is called RelBoost. And the main idea of RelBoost is to overcome feature explosion by aggregating learnable weights. So what we have done in all of the algorithms before is that we have done an aggregation over some sort of column. But the idea of RealBoost is to say, well, let's not do that. Let's instead aggregate some sort of weight that we would be able to calculate using math and statistics. And then the columns can only be used for the conditions. So that means if we have 10 columns, well, there are 10 conditions we could build here. And if we have 100 columns, there are 100 conditions we could build here. And that means that the feature space actually grows linearly with a number of columns, not quadratically. And that means that RealBoost doesn't have the problem of feature explosion, and it therefore scales to data sets with many, many columns. And this is actually a very, very big plus. This is a very big strength about RealBoost. So RealBoost actually, much like all of the other algorithms that I've shared with you, works in a tree-like greedy algorithm. So you pick an aggregation, you try different conditions. For each of these conditions, you then calculate the optimal weights. You keep the best condition that minimizes your optimization criterion, and then you go back to step 2 until some sort of starting criterion is better. And then on top of that, as the name implies, you could also use gradient boosting. And gradient boosting, as you might be aware, is again also one of the most successful machine learning paradigms out there. I mean, at the beginning of this talk, I've mentioned algorithms like XGBoost, like CatBoost, like LightDB, and all of these things are based on gradient boosting. So this is just again taking a very successful machine learning paradigm and applying it to relational data, the problem of relational feature engineering. So let's talk about the pros and cons of RealBoost. So the first pro is you don't have feature explosion. That's a very big strength of RealBoost. You can build any number of features. Again, it's an ensemble learning algorithm. And again, this builds on state-of-the-art machine learning paradigms. But there are disadvantages as well. So the first thing is it doesn't allow for more complex aggregations. Like for instance, if you want to do count distinct aggregations, it is very, very difficult to calculate the weights if you have a count distinct aggregation. Or median aggregation, same thing here. It's not really straightforward to calculate the weights there, and that's a bit of a problem. And the next thing is it is harder to interpret because the features are going to be pretty far away from something that you would build by hand. Okay, there's one more algorithm that I want to share with you. And this actually extends RealBoost in a way, and it's called ReLMT. ReLMT is short for a relational model tree. And first of all, I should have to explain to you what a model tree is. So the idea of a decision tree, a very normal decision tree, is that at the end, at the leaves of the decision tree, you've got some sort of value, you've got some sort of weight that you would have to calculate based on the target variable. But with a relational model tree, it's a bit different. With a relational model tree, on the leaves, you have some sort of linear model. With a model tree in general, you have some sort of model, and usually that is a linear model. And the idea of a relational model tree is to take this concept of a model tree and then apply it to relational learning as well. So on the leaves of the relational model tree, we would have some sort of linear transformations over the original columns. Okay, let's talk about the pros and cons of a relational model tree. Again, you don't have feature explosion. Feature space is just as large as you would have it for RealBoost. Again, you can build any number of features. It also builds on gradient boosting, just like RealBoost does. And it's actually very well suited for time series problems. And I will get to that in just a second. On the con side, again, it is not as scalable as RealBoost because calculating these linear models is actually far more expensive than calculating a single weight as you would have RealBoost. And it also doesn't allow for more complex aggregations like count distinct and median, just like the same problem as with RealBoost. Okay, what I want to do in just a second is a live demonstration. But before I get to that, are there any questions about everything that I've covered so far? Yeah, I'll just leave that because I don't want to create this endless thing there. Okay, Are there any questions? Is there anything? Okay. I'm a bit surprised by that. I thought there'd be questions, but okay, never mind. If that's the case, what I want to do is to get straight to the live demo that I've brought for you. So what I will do, this is an IPython notebook that I've prepared for you, and this is all live. So I'm going to start the notebook now, and while the notebook is running, I will explain to you what this problem is about. So as you might have gathered from the title of the notebook, is that the idea here is to predict air pollution in China using relational learning. So this is a public domain data set, and the idea is we have a measurement of PM 2.5 concentration in Beijing. Just in case you wonder what PM 2.5 is, this is what we in Germany call Feinstaub. So this is what this is all about. And if you've ever been to China, you would know that this is actually a big problem over there, much more than it is in Munich. So that's the first thing. As our input variables, we would have things like wind speed and temperature and air pressure and time of the day and so on and so forth. So based on these sort of very straightforward, easy to get variables, we would like to be able to predict the air pollution in China. But also,
Patrick?
yes.
Sorry to interrupt shortly. We got a question. Can you zoom in, please?
Can I zoom in? Of course.
Let's check if that is better, Firas, for you also, or maybe the others. Just type it in the chat.
I can't see the chat. I can only see my.
Okay, much better.
Much better.
Nice.
Okay.
There you go. Thank you.
Happy to hear that. Okay. Very good. Okay. So yes, like I said, the idea is to predict air pollution in China, but there's no past data that is allowed. So in a classical time series problem, what we might do is maybe look at the air pollution from 1 hour ago, and then we predict the air pollution maybe in 1 hour. But I thought that's a very boring problem, because I feel, well, if I know what the air pollution is now, then predicting the air pollution in 1 hour really isn't that hard. What is much more challenging is to predict air pollution from other variables. And I think, in terms of general usefulness, I think this really makes a lot of sense as well, because in China, air pollution is a bit of a sensitive topic politically. And this data set was actually collected at the United States Embassy in Beijing. So it's just this little spot of America within China where this was measured. And there's a reason why it was measured at this particular location. Okay, so because this is a nowcast, this really isn't a forecast, and we don't allow lag targets, we don't really have an autoregressive component, it is not really obvious how you would use classical time series analysis like REMA for that, because the AR in REMA stands for autoregressive. But for relational learning, it's actually not a problem at all. For relational learning, that really doesn't make a difference at all. Another thing about time series, classical time series analysis, is that they often assume that the data is measured in equal, that there's equal spacing in terms of time between the data measurements. And that often, that assumption is violated, particularly when we talk about sensor data. But again, relational learning doesn't make this assumption, and you don't really have to have this kind of data in order for relational learning to work. So that is why I say that relational learning is actually a very, very good approach to time series as well. This is just more flexible, and you can use it in any kind of time series you want to. And in fact, if you take a look at tools like TSFresh and H2O, both of which are quite popular, their approach to feature engineering for time series is exactly that. They just apply relational learning to the problem of time series. Okay, so can I scroll? Yes, I can scroll. There you go. So the first thing that we do is actually load the data, but that actually isn't terribly interesting. So we'll get straight to building the data model here. So this is basically how we can build a data model in a relational learning context. By the way, just so you know, this is obviously my own tool, but again, there are many other tools out there there's feature tools, there's TSFresh, there's H2O and whatnot. I'm obviously going to use the tool that I'm most familiar with, but whatever tool makes you happy, I'm fine with. Try them all out, figure out what works best for you, and I'll be happy with that. Okay. So again, I just quickly want to get into how you can build a data model for something, a relational data model for something like a time series. So what we're going to do here is we're going to take a look at the main table, and then we will join that table onto itself. So the kind of features that we will build is, okay, give me the average wind speed in the last 24 hours. Give me the maximum wind speed in the last 24 hours. Give me the median wind speed in the last 24 hours. Give me the maximum air pressure in the past 24 hours, and so on and so forth. So these are the kind of features that we would build here. And the first thing that we would do is a propositionalization approach, because this is, of course, the simplest approach that we have. So the first thing that we would do is propositionalization approach, and this actually has already run through. It took some 24 seconds. And now we can actually take a look at the kind of features that we've learned. Okay. So where's, yes, sorry about that. There you go. So this is the propositionalization approach. I've been talking for too long because now the other approach has already gone through. Okay, never mind. So let's take a look at the features that we have. So the features are, the screen is now much bigger than it usually have. But okay, there you go. So yeah, first of all, can everybody see the SQL code that we have here? So this is the most important feature that we have. If for some reason you've got trouble seeing this, just write it in the chat and then Lara will interrupt. So this is the most important feature that we have built using propositionalization. So this is something that is very intuitive. It just takes the dew point. This is what dew stands for, it's the dew point. It takes the last dew point measurement that we have in the past 24 hours. Then, of course, we also have IVS, that's the wind speed. So we've got the median wind speed over the past 24 hours. This is the second most important feature. Then the third most important feature is the maximum wind speed over the past 24 hours. Then also we might have the standard deviation of the dew point over the past 24 hours, and so on and so forth. So the takeaway from this is that, well, yes, these are the kind of things that you could have done by hand. Of course, like if I were to ask you to prepare a set of features for me, this is probably what you would have done. This is probably what you've done by hand. This is the kind of features you would have built manually. But you probably would not have been able to build 72 features in 24 seconds, as this automated approach would have done for you. And of course, there are other tools that you can use for that, like feature tools and so forth. So yes, so this is, you can already see how even though you could have done this by hand, and these are very simple features, how something as simple as propositionalization would end up saving a lot of time. Let's go back a bit and see how we actually did that in terms of our predictive accuracy. So propositionalization, this is the first thing here. It has an R squared of 51.14%. So 51.14%, and we have an RMSE, which is the root mean squared error, of 65. So that's just about what we get there. And an R squared of 51% means that we can explain over half, over 50% of the variation in air pollution using these very, very simple methods. Okay, the second algorithm that I want to share with you that I've used is Relational. That's the last algorithm that I shared with you. And as you can see, the fitting took much longer. So for the propositionalization approach, we got this done in 24 seconds, only under 30 seconds. But for the Relational, it actually took 10 times as long. It took almost 5 minutes to complete this problem. And I've been talking for so long, so it didn't really matter. But yes, I mean, of course, this sort of runtime matters. And there is a big difference between these sort of more advanced, more complex approaches and very simple propositionalization. But there's actually something that we get in return, because if we take a look at how well we did in terms of our R squared, what we can see is that we got over 60%. We got 62.3% of our R squared. So that's more than 10 percentage point difference in terms of the predictive quality. This sort of difference is really, really going to matter a lot. So this sort of increase in predictive accuracy, yeah, that is really something where it is worth using these sort of more advanced approaches that we have as well. But other than runtime, there's another price that we pay for that. Remember how I just showed you the features? And the features were very, very simple and very easy to interpret. Well, you know, for Relational, it's not quite like that. For Relational, we've got these very, very complex case-when statements, like, well, if the wind speed is greater than 3, and also the date is smaller than some other date, and the dew point is greater than 1, and at the end of the feature, we have some sort of complex linear model, which, you know, with very weird weights. I'll move there, but yes, I'll move there. So yeah, I know that there's a bit of delay with you guys, you see this, but what I was hoping you'd see there is, yeah, this is sort of complicated. This is sort of harder to interpret than the very simple features that we had a second ago. And the same thing here. So if we take a look at the second feature, this is also, again, something that is actually quite complex. This is not something that you would ever build by hand. You would actually need an algorithm to build these sort of features. But on the other hand, yeah, you get something in return. You get greater predictive quality. So let's go back to the slides. I've just done a little live demonstration on a simple data set. And even though this is quite a simple data set, there are many, many important takeaways that we can get from here. What I would always recommend is that the first thing that you should do, no matter whether you do machine learning or really anything in life, is to try the simplest solution you could possibly think of. The simplest solution you could possibly think of in our case is obviously propositionalization. So that is always the first thing you should do. And then if you find that for your particular data set, propositionalization actually does a very good job, and there are many data sets where propositionalization actually works quite well, you stick with that. You know, we data scientists, we often have this impetus. We want to try the fanciest approach out there and the most advanced thing that we could possibly think of. But really, at the end of the day, particularly, you know, in software development, what you learn is, well, if a simple solution gets the job done, you should really stick with a simple solution. You shouldn't go for fanciness and advanced algorithm just for the sake of fanciness. So again, the first thing you should do is propositionalization. You try the simplest approach. And then if that works well, you stick with that. And then if you find, well, actually there are more advanced approaches that get you much better results, as we have in this case, well, then maybe we should go for the more advanced approaches. And of course, what you can always do is you can do both. It doesn't have to be either or. You don't have to use just one approach. You can combine as many approaches as you want to. You can maybe build in one or two handcrafted features as well if you want to. Whatever works for you, that's really the best way to go forward. Okay, so I want to conclude this with a couple of remarks other than those that I've just made. I really hope that the takeaway that you get from this, if there's one thing that you take away from this, let it be this. You don't have to do manual feature engineering. If you approach a relational data problem or a time series problem like that, there really is a better alternative to manual feature engineering, not only in terms of time, but also in terms of predictive accuracy, in terms of quality. Because, I mean, these sort of simple propositionalization approaches, they pretty much cover what you would probably do by hand anyway. So these are going to be just as good as what you can do by hand, only faster. But then on top of that, we also have more advanced approaches. So these kind of approaches and this kind of thinking, relational learning, would, by the laws of logic, you would expect this to be at least as good as something that you could do by hand, but only much faster. So yes, please do give it a try. There are many, many tools that I've mentioned. You know, try them all out and see what works best for you. There really is an alternative in the year 2020 to manual feature engineering and you should really use that. Yes, so that's my talk for now, and I'm very, very happy to answer your question. Thank you very much for your attention.
Thank you so much, Patrick, for the talk, and feel free to give him a virtual applause, either by doing the reactions or by pressing Z